Good afternoon. During the last lecture, I presented two global theorems, the first of which was the Hopf Umlaufsatz, which says that the rotation index of a simple closed plane curve is 1 or -1. Today we will try to see the generalization of this theorem to another class of curves known as piecewise regular curves. In order to do that, I need several definitions. So the first one is definition of piecewise regular curve, and in the sequel I will use the following acronym. I will write, instead of piecewise regular, PWR. So a PWR curve in Rn is a continuous function gamma defined on a closed interval AB with values in Rn with a partition A equal to T0 smaller than T1 smaller than T2 smaller than Tn, which is equal to B, such that the restriction gamma I of gamma to each sub interval Ti plus 1 is a regular curve. The curve defined this way, it is closed, it is called closed if additionally we have gamma A equal to gamma B, and it is called simple if gamma is 1-to-1 on the domain AB, closed on the left and open on the right. It's not finished. It is said to be of unit speed if each gamma I is of unit speed. This definition says that there exist finitely many times at which gamma is not smooth but only continuous. Another remark I want to make is that the definition of closed does not require that the derivatives of gamma at A and D match. We require only that gamma A is equal to gamma B. So this means that the point t equal to A can be one of the non-smooth points. The next definition I need is one of positively and negatively oriented curve. So PWR simple closed plane curve gamma is called positively negatively oriented if the vector R90 gamma prime t points toward the interior for all values of t that correspond to smooth points. Instead, for the definition of negatively oriented, I will just write that they point toward the exterior. So I mean that if R90 gamma prime points toward the exterior, then the curve is negatively oriented. The next definition I need is definition of corner So let gamma from AB into R2 be a piecewise regular plane curve with the partition denoted by A equal T0 is more than T1 is more than T2 is more than Tn equal B. Then each non-smooth point gamma Ti is called a corner of gamma, and we also observe that at each corner there are two velocity vectors. So at each corner there are two velocity vectors. The first one is denoted by V minus Ti, and this is the limit as h tends to 0 minus of gamma Ti plus h minus gamma Ti over h. This can be also written as a limit as t tends to Ti minus of gamma prime t, and there is also V plus Ti. This is the limit as h tends to 0 plus of gamma Ti plus h minus gamma Ti divided by h. And in the same way, this can be written as the limit as t tends to Ti plus of gamma prime t. The next definition is definition of signed angle. The sine angle at gamma Ti denoted by alpha Ti is a number which belongs to the range minus pi and is defined such that its absolute value equals the smallest determination of the angle between V minus Ti and V plus Ti, which are the vectors I introduced here. What is now the sign of alpha I? The sign of alpha I is positive if V plus Ti is a counterclockwise rotation of V minus Ti through this angle Instead, it is negative if the rotation is clockwise. So, for example, if this is the trace of gamma, and we suppose we travel on it according to this direction, then we have that this is the vector V minus Ti. Instead, this is the vector V plus Ti. And in this case, V plus Ti is obtained by V minus Ti by a clockwise rotation. So this means that alpha I in this case is negative. Instead, in this case here, we have that V minus Ti plus 1 points this way, and V plus Ti plus 1 points this way. And it is easy to see that V plus Ti plus 1 is obtained by V minus Ti plus 1 by a counterclockwise rotation. And this means that the sign of alpha I plus 1 is positive. There is a special case of corner. So special case. The corner gamma Ti is called a cusp if V plus Ti is a negative scalar multiple of V minus Ti. From this definition, it follows that alpha I can be equal to pi or minus pi. So precisely alpha I is pi if V minus Ti. Okay, let's write it. Alpha I is pi if V minus Ti points toward the exterior, and alpha I is equal to minus pi if V minus Ti points toward interior. So let's see one simple example. So this is a simple closed curve with two cusps. Suppose that we travel along the trace of gamma along this direction. Then we have that in this case we have that V minus T1 points this way, and V plus Ti points T1 point this way. So in this case we have that alpha 1 is equal to pi because V minus T1 points toward the interior. So we are in the second case, sorry, minus pi, because we are in the second case. Instead, at this cusp here, we have that we have one vector pointing this way and one vector pointing this way. So precisely we have V minus T2 and V plus T2, and the alpha 2 is exactly pi because we are in the first case. One remark concerning the endpoints of the interval AB. So if gamma is closed and gamma prime A is different from gamma prime B, then gamma A is a corner, and in order to find the corresponding sine angle, we have to use V minus B instead of V minus A. Why? Because of V minus A is not defined. Okay, now I'm ready to present the statement of the generalized Hopf Umlaufsatz which says the following. So suppose that gamma is defined on a closed interval with values in R2 and to have a unit speed to be positively oriented to be a piecewise regular simple closed plane curve, then if Ks denote its signed curvature function, and let alpha I be the list of signed angles at its corners. Then we have that the sum on I from 0 to n minus 1 of the integral from ti to ti plus 1 of kst dt plus the sum on I from 0 to n minus 1 of alpha I This must be equal to 2 pi. Let's see how this theorem reduces to the basic version of the Ops Umlaufsatz when the gamma is irregular. It's very easy to see that. So if there are no corners, that is gamma is regular, then we know that there exists a global angle function of gamma denoted by theta such that Ks is equal to theta s. This is a result we proved in the past. As a consequence, instead of writing Ks tdt, we write theta prime t dt, and we don't have this sum of integrals, but just the integral from a to b. And what is this? This is theta b minus theta a, because there is no such a term. If there are no corners, this term disappears, and this is equal to 2 pi times rotation index. So this result combined with this one, precisely look at the right hand side, we have that 2 pi must be equal to 2 pi times the rotation index, and this implies so by comparison we get that the rotation index is equal to 1. This is exactly what the Ops Umlaufsatz says, because we are considering a positively oriented curve, and for this kind of curves the rotation index is 1. Now I want to present briefly the reformulation of the Ops Umlaufsatz in terms of interior angles. So what are the interior angles of a curve? So once again, suppose that gamma is defined on a closed interval AB with values in R2, and it is piecewise smooth. Simple and closed. And suppose that the sine angle are denoted once again by alpha I. Then the ith interior angle of gamma denoted by beta I is a number in the range 0 to pi, given by I should write is given by the following formula: beta I is equal to pi minus alpha I if gamma is positively oriented, and it is given by pi plus alpha I if gamma is negatively oriented. Now let's see how the ops umlaut looks like if instead of using alpha I we use beta I. So the original form of the theorem is the sum on I of the integral from Ti to Ti plus 1 of Ks T T plus sum of alpha I on I. This must be equal to 2 pi. But alpha I, if gamma is positively oriented, then from this formula we get that alpha I is given by pi minus beta I, and if we replace this formula for alpha I into this identity, we get sum on I of the integral from Ti to Ti plus 1 of Kst dt. This is equal to sum on I of beta I minus n minus 2 pi. The term minus 2 pi comes from the term 2 pi you have here, and the term beta I minus n sum on I beta I minus n pi comes from this sum here, where you have to take into account the fact that you have n corners. So from this term here you will get n pi. I want to consider a special case. So special case is one where the smooth segments of gamma are straight line segments. So in this case we have that k as t identically 0, and we get that sum on I of beta I is equal to n minus 2 pi. This is a formula you probably already know. Precisely when you have a polygon, you know that the sum of the interior angles of this polygon is equal to the number of the edges of the polygon minus 2 multiplied by pi. Okay, now let's change topic. And let's study the material contained into the section 3.1, derivative of a function from Rm to Rn. Okay, suppose that U is an open set over M So when I write this way, I mean a function defined on such an open set with values in Rn. In this case, f must be thought as n separate component functions functions, and each component function, of course, is defined on U, but it takes value on R. So for example, if we take f of xy defined on R2 with values in R3, defined by f of xy equal to sinus of xy e power x plus 5y x squared y cube. We have that the component functions are sinus of xy e power x plus 5y and x squared y cube is the last one. Okay, let's talk about now partial derivatives. So the partial derivative of f with respect to xi. Okay, let's write to the input variable xi is defined in the following way. So for all p in u, then f of xi, sorry, fxi p or df dxi at p, these are two possible notations. This is defined as the limit st tending to 0 of f of p plus tei minus f of p divided by t if these limits exist. And here ei in Rm denotes the ith member of the standard orthonormal basis please observe that since f has n component functions, also the derivative has n component functions. So we have that df dxi at p we have this identity. Now let's suppose that I is fixed. So for fixed I, if df dxi p exists for any p in U, then the function which associates to the point P df dxi at P is affine on U and has values in Rn, exactly as the function f. This means that we can take the second order derivative of this function. Sorry, we can take the derivative of this function, which will be the second order derivative of f. Its derivative actually its partial derivatives if they exist are the second order partial derivative of f. In the same way, in a similar way, we can define the higher order partial derivatives of f. I would like to mention an interesting result. Mixed second order partial derivatives coincide. This sentence means that d second f dxi dxj is equal to d second f dxj dxi if both sides of this identity exist and are continuous. Okay, I will give you very briefly a list of functions which are smooth on their domains. So functions which are smooth. What does it mean, this word? This means that for any positive R, Rth order partial derivative exists and are continuous on U, on their domain. These are polynomials rational functions exponentials logarithm trigonometric functions and inverse of trigonometric functions. It is also possible to prove that some difference product of smooth functions on a same domain is a smooth function on the same domain. There is another operation that you can do with smooth functions, and it's a composition. So precisely we have this proposition if G is a function defined on an open set U of Rl with values in Rm is smooth on U, F is a function defined on an open set V containing Rm with values in Rn is smooth on V, and you have that G of U is contained in V, then the composition F composed with G defined on U with values in Rn is smooth on U. Now I want to introduce a notion which generalizes the definition of partial derivative. It's the notion of directional derivative. So suppose that F is a function defined on the open set U of Rm with values in Rn. Suppose that P is a point in U and V is a vector in Rn. Then the directional derivative of F in the direction V at P is denoted by dFPV, and it is defined as the limit st tend to 0 of f of p plus tv minus f of p divided by t if the limit exists. This definition can be reformulated in terms of curves. Formulation in terms of curves. Precisely, if we set gamma t to be p plus tv, then dFPV can be defined as the composition of f and gamma of which we take the first derivative and we evaluate it at 0. So this definition here says that df/tv is the initial velocity of f composed with gamma. Of course, if we take v equal to ei, then the directional derivative gives us the partial derivative. Okay, the next result I want to present is a proposition. Precisely, it's the proposition 3.4, which says the following: if f defined on U open set of Rm with values in Rn is smooth on U, then for all P in U we have the following: 1. df/Pv exists for all vectors V in Rm. 2. The map which associates to V the directional derivative of f in the direction V is a linear map from Rm into Rn, which is called the derivative of f at P. And number 3, f of q is approximated by f of p plus dfp evaluated at q minus p, and this is a good approximation, of f near P. Please observe that In this formula, Q minus P must be interpreted as a vector, okay? Okay, so this proposition says that the DFP is a linear map. What is the matrix which represents this linear map? The answer is provided by proposition slash definition 3.5. It says that if F is defined on new open set of Rn with values in Rn, is smooth and P is a point in U, then DFP is LA, where LA means the linear map associated to the matrix A, where A is the n times m matrix given by the following formula. A equal to df1 dx1 at p df1 dxm at p dfn dx1 at p dfn dxm at p. This is what we call Jacobian matrix of F at P. You already studied the case when n is equal to 1. So special case, n equal 1. In this case, we have that A is just df dx1 at P, df dxm at P, and this is the gradient of F at P. The unique difference is notational because this is a 1 times m matrix. Instead, you are used to express to see the gradient as a vector. So if V is, for example, V1, V2, Vm, then df PV is given by LAV. That is, I will continue here. The product of df dx1 at p df dxm at p multiplied by v1 v2 vm. I have to write this vector this way, so I interpret v as a column vector because I need to be sure that this product makes sense. And this is the sum on I of df dxi pvi. That is the inner product of gradient of f at p and v. Okay, next thing I want to mention is the proposition 3.7, which says the following: if f is a function as usual defined on an open set U of Rn with values in Rn is smooth, and V is a vector of Rm and gamma is any regular curve in U with gamma 0 is equal to P and gamma prime 0 equal V, then we have the following formula: df P at V, this is F composite gamma prime evaluated at 0. So this formula has been already presented a few minutes ago. The difference with this proposition is that before, when I define it, we have chosen gamma t equal p plus tv. Instead, here we are saying that the gamma is any curve such that gamma 0 is p and gamma prime 0 is v. So the same formula holds true. Okay, let's see an example. In this example, I will change the notation. This will be useful in the sequel of this course. So example 3.8. In this case, we look at in this case we have m equal to 2 and n equal 3. And let's take a map sigma defined on R2 with values in R3. Suppose it to be smooth and assume that the component functions are x, y, z, then let gamma be a plane curve in the UV plane. I think it's clear that in this example v is not a vector, it's a variable. With component functions denoted by gamma t equal ut vt, then previous proposition says that I don't erase it, I will keep the formula. Says that the differential of sigma at gamma t evaluated at gamma prime t, this is sigma composed with gamma prime evaluated at t. How can you get this formula? Just replace P by gamma t, V by gamma prime t. And 0 by t. This can be written in the following matricial form. So sigma composed with gamma prime remember that gamma t was a ut vt and sigma uv was a function whose components were x uv, y uv, z uv. Then what happens if you compose a sigma with gamma? You get xu, xv, yu, yv, zu, zv multiplied by u prime, v prime, and this can be written as u prime sigma u plus v prime sigma v. This is the Jacobian of sigma. Okay, the last result I will present today is the chain rule or proposition 3.9. So suppose that G is defined on an open set U over L. It takes value in Rn. Suppose also to be smooth. On U. Suppose that F is defined on V open set of Rm with values in Rn. Also this function must be smooth on V, and G of U contained in V. Then for all Q in U, we have that D of the composition of F and G evaluated at Q is equal to dF P composed with dG Q, where P is equal to GQ. This formula allows you to prove the following result. The derivative of an invertible function is an invertible matrix. How to prove it? So suppose that F is a function defined on an open set of Rn with values in Rn. Please note that we are considering the same space. And this function must be invertible from U to F of U. Suppose that F is smooth on a neighborhood at least of Q in U, and F inverse is smooth. Unfortunately, I have to erase this formula. On a neighborhood of F of Q. Then the chain rule says that the derivative of f inverse composed with f at q, this is the composition of derivative of f inverse at f of q composed with the derivative of f at q. So I use this formula, I got this formula using the chain rule. So use the chain rule with G equal F, F replaced by F inverse. And I should mention also about the point Q. Here we have that P of course is f of P. So please don't be confused when I write this way. This means that G is replaced by F and F is replaced by F inverse. What is the consequence of this formula? F inverse composed with F is the identity function. So the derivative of the identity function is the identity map. So this is identity map. And what do we have on the right hand side? We have that the composition of these two linear maps is the identity, implies DFP is an invertible linear transformation and its inverse is exactly this one. Okay, for today that's all. Thank you for your attention.